Right. We'll do another example for this topic on tributary area, but this example will be kind of different, I mean slightly different than the ones that we did earlier. So in this problem we have this. We have a frame. And we have columns here, 6 columns, and then we have girders, girder 1, girder 2, and then girder 3. And then the rest, there's beams. So meaning that this beam is just resting on the girder 2. And this beam, another, I mean the support reactions here, or let's say this joint, this boundary conditions um, is a point load on these girders. Okay, so we're given this distance 7.5 meters, 7.5, 3 meters, 3 meters, 3 meters. So it's pretty uniform spacing. Okay, and the given are 400 by 600 beam cast monolithically with a 100 thick slab. Okay, and we have this superimposed dead load. So, for example, if we have a superimposed dead load, then it means that, for example, this could come from, let's say, electrical facilities, or let's say tiles, probably, or others. Okay, and we're also given this live load of 3.6 kilopascals. So of course, once you're given these dimensions, then meaning that you need to solve for the dead loads by the structural members itself, and then you'll add up the superimposed dead load. So if you're given this, and the dead load is not given, then you need the unit weight of the weight density of concrete, which is 24 kilonewton per meter cube. So if we need a unit of kilonewton per meter for the distributed loadings, then what we need is the area. So usually it's the cross-sectional, or the area at the cross-section. Okay, so we are asked to find the max shear and max moment of girder 2. Okay, so that's right, solution. Okay, so for our solution, now let's solve. Okay, let's plan first. So how do we get this loadings right here? So since this is a girder, then the loadings would be from the slab to the beams, and then from the beams to the girders. Okay, so since these are uniform spacings, then we can actually just solve. Just actually once, let's say one beam, and then the value would just be the same. Okay, so for now, let's solve for the ratio. Okay, slab ratio. So we have Ly over Lx, that's 7.5 divided by 3 is equal to 2.5, which is greater than 2. So therefore, it's a one way. Okay, so meaning this load is right here, it's just one way. Okay, so if this is half, it's 1.5, and then another half on the other side, that's 1.5, so a total of 3 meters. Okay, so solving for, let's solve now for total dead loads. Okay, so we'll illustrate for now. We have this slab that's cast monolithically with the beam. So this is how it looks like. Okay, our slab okay, so this is our slab, and we have 100 thick, And our beam is actually from this point to this bottom point. That's we have a 600, and the bottom width of this beam is 400 mm. Okay, so if this is 600 and this is 100, then you have a 500 mm difference. Okay, so for the dead load, okay, so dead load of slab. Okay, so for the dead load slab, we have a actually what we need is the cross-sectional area, because we have a unit weight times the cross-sectional area. Okay, so what is this? This is 24 kilonewton per meter cube, and then the cross-sectional area. Okay, so the cross-sectional area is from this point to this point, so that's the tributary width, which is just 3 times this this thickness, so 0.1 3 times 0.1 meter squared, so that's gonna be 7.2 kilonewton per meter. Okay, so 7.2 kilonewton per meter along this beam length. Okay, now let's solve for the beam. Okay, so for the beam, since it's a concrete beam, then again it works the same way. Okay, now for the beam, okay, we'll just write again 24 kilonewton per meter cube times the cross-sectional area. Okay, so since we already considered this area right here, so the computation for the beam, we'll just use this one. Okay, so the remaining area, which is 500 by 400, so that's 0.5 by 0.4, and what you get is 4.8 kilonewton per meter. And our superimposed dead load, let's say superimposed dead load, that's given already, so that's 3.2 kilopascals, so times the tributary width, and what we get is 9.6 kilonewton per meter. Okay, so now we can solve for the total dead loads. Okay, total dead loads, therefore, is just simply the summation of the dead loads. Okay, so we have d sub s plus d sub b plus the given one. Okay, which is 7.2 plus 4.8 plus 9.6, get a value of 21.6 kilonewton per meter. Okay, so that's our total dead loads. Now for our live loads, this is solving now for live loads. So L is equal to 3.6, 3.6 kPa, so times the tributary width, which is 3 meters. That's going to be 10.8 kilonewton per meter. Okay, and then now solving for factored loads. We get U is equal to 1.2 dead plus 1.6 live. So 1.2 times 21.6 plus 1.6 times 10.8, we get 43.2 kilonewton per meter. Okay, so therefore, to illustrate that, this beam, or let's draw the three-dimensional view. I think that's better. Okay, so let's say this is our girder. So we have this (43.2 kilonewton per meter). Okay, so if we try to solve this reaction, what we get is so solving for reactions. So R is just simply the shear value, which is WL over 2, so 43.2 times what's the length? That's 7.5 divided by 2. Okay, so 43.2 times 7.5 divided by 2, and we get a value of 162 kilonewtons. Okay, so meaning that the girder this is girder B. Girder B. So so meaning we have a reaction of 162.2 from one beam, and then another 162.2, then on this beam there are two reactions. So finally we can draw let's say, okay, we'll just write drawing the girder 2. So if we draw that, let's say we have a simply supported beams, then we have 162 times 2, that's 124 kilonewtons, then 124 kilonewtons. And this one is 3 meters, 3 meters, 3 meters. Okay, so if we draw the shear moment, okay, I have to draw it again here. Okay, so we have shear, then we have moments at the bottom. It's a moment diagram, a shear diagram. Okay, so if we draw the shear diagram, it will look something like this. Okay, so first you solve this one, which is just equal to 324 because they're just equally spaced. Okay, so you get this. Okay, go up, and then since there's no shear loads, then that's going to be constant. then there's a shear loads here, so go downwards, then constant again at this point. So it's like we're starting here and then we're moving towards the right. So up, constant. Okay, it says go down, so go down, then constant again, nothing happens, and this point it says okay, go down. Okay, 324. Okay, so something like this. So that's gonna be the shear. Then for the moments, it's just simply the area. The change in moments is simply the area of this shear. So something like this. Okay, so that's gonna be a different case or a different story if we'll deal with indeterminate structures. Okay, so that's all that I'll discuss. I mean, there's still other load transfers that I was not able to discuss, such as, or I need to do examples with, like for example, the the walls on the warehouse structures that's attached to the columns. Okay, anyways, I think that's enough for the sample. Now I'd like to discuss the homework number 3. So I'd just like to give an overview or something like a run through of this. Okay, so this is our homework number 3. So that's the due date is on March 5. Okay, so that's gonna be next week, Friday next week. Okay, so general instructions, and then this is our homework. So consider swine housing as shown below. The structure is a simple frame with truss roof. Okay, the truss roof supports purlins, which supports corrugated GI sheets of 0.8 mm thick. Okay, so there's a reason why I specify this thickness, because you're gonna have to refer to the tables to get the values of the dead loads, or let's say the unit weight of such materials. Okay, the truss is supported by 4 columns made of GI pipe, 3 inches diameter, schedule 40. So again, there's a reason for that. And then the exterior columns are the ones connected to the foundations or footings. So we have 4 columns here. The truss supported by 4 columns, but only the exterior columns are the ones transmitting the loads to the foundations. These 2 columns right here, they're just actually transmitting their loads to the floor beams, to the girders. Okay, so the reason for this hollow area here, or hollow, or something like a volume, is just, it's the manure pit, or designed as a storage or manure storage or something. Okay, and then from the finished floor line, the truss elevation is 2.4. So from here to here, that's 2.4 meters. So you can refer that to pass 401 for the details. Then the height of the pan wall is 1.2 meters. Okay, so from this to this, that's 1.2 meters. So again, you can refer to pass regarding the height of floor lines. That depends upon the type of swines, like for example, is it a boar or finisher or something. So you can just refer to that. But for here, we use these values. Okay, the floor system is a slatted floor system and is elevated for the manure pit storage systems. To determine the factory loads of each structural members along, B, draw the loading diagrams and calculate draw the shear, whichever is applicable. Okay, so this is the floor framing plan. So the floor framing plan, we have, these are the columns, and we are just asked to determine this the loadings of the structures connected along this B, this section B, or point or balloon B. Okay, so we have an aisles here, and these are pen walls, right? Pen walls. Now beneath the pen walls, they're actually supported by a beam. So these are floor beams. Okay, floor beams. Now for the roof plan, so it's just like this. We have a roofing sheet and then purlins. Okay, so we also have eaves beam, but what I'm just after in this homework is just the loadings along this section. Okay, and we have the truss details. So for the truss, we have this let's say the distances between these web members, the vertical web members, 0.75. So 0.75, and then a height here is 0.75. So you can plot this out in the software. Okay, so we have dimensions as well, 7.5, then 6 meters bay width. So you can follow that up. Okay, so for the cross section, so this is it. It's just the same, I guess. And the data. So the data, we have the deadloads here. So for example, the roofing sheets. So if it's not stated here, then you have to find that out from the attached tables or attached sheet. Okay, and of permanent self-weight, I managed to find that one for you. So that's already given 0.202 kilonewton per meter. Truss deadloads. So for the truss deadloads, you recall that we had an empirical equations for steel truss or timber truss. So I'm not sure which one is for the steel truss, but there's an equation that's given in imperial units. So you have to transpose the units into the English units so that you can use these equations, and then just transpose it back. Okay, so once you have this, then it's gonna be fine. But I think, if I remember it correctly, I think this equation will give a value of probably something like a single load or something. So we'll just discuss this, how to make that into, or how to transpose that to a distributed loading or something. All right. What else? Okay, so for the steel pipe and then the pen wall, so since we have a 100 mm concrete, then it's also available in this data sheet. And then for floor slabs, so recall that this is the design of this swine housing is actually it's designed to have a slatted floor, so that the waste, wait, no, not there, I guess it's here. Okay, so that the waste, okay, we'll try to draw. Let me draw the, okay, so that's our swine right here. Okay, so that the waste will just fall into this pit. Okay, so even though it is slatted and there are details for the slat dimensions, in our calculations or in our homework, we'll just assume that it's solid. Okay, so just assume that it's solid, and then for the beam dimensions, we just assume that we have 300 by 500. Then for the girders, assume a 400 by 600 or something. Okay, so I think this is it. The beams, and then we'll just use. Alright, so for this larger girder dimensions, that's for B-3, and for this you can use this for, let's say, B-2, and then B-1. Okay, so why is it larger? Simply because we have a loadings from this steel post. So the loadings is actually transferred to this. So basically the beam is the one that carrying this this column. Okay, so it has to be strong enough to be able to carry the loads. Okay, so that's the homework. And then just for easy life, so just make this something like this. Okay, so you just have to fill out these boxes here. So for example, the truss dead load, so what's the value? So you can actually see the box here if you print our homework. And then our dead loads from the purlins and from the roofing sheets, that's distributed. But recall that in truss analysis, we only use point loads in the trusses, and the points are actually in the joints here. So the technique is to cut this into tributary width, and this tributary width, right? So this is for example, the tributary width, and then you transform that into one single load or point loads, something like that. Okay, and you have these support reactions. Then probably we'll just use a pin, and then what's this, roller and roller supports, and then just input that in the software and try to strive we can get results. So once we get the results, then we can get once we get the reactions, then meaning that we have the loadings for the steel columns. Okay, so that steel columns will then be transferred into this let's say the columns beneath the floor beams, or for interior columns for the case, then the loads will be transferred to the beam, right? So take note that once you transfer the loads, you also have to include this loadings from the dead weight of the steel pipe. Okay, so that's it, you have to include. And then from the flooring, we have this distributed loads. So you'll just apply what we've learned in the previous videos. So you just apply that, and then you can get this diagram. So of course you have to be careful in the load transfer process. You have to be it has to be proper, right? And you notice that at these sections it's expected it's larger simply because there's a wall, but in this section along the aisles there's no wall. So I just highlighted that out. Okay, and then after that, once you have this diagram finalized, then you input in software, try to, if you can get values in the reactions. Okay, so that's all for our homework. I guess we're done with the topic on structural loads, including the types of loads, and then the tributary areas, the load combination, stuff like that. So in the next video, we'll be delving into the mechanics of the reinforced concrete structures. Okay, so see you next time.